The problem statement from GATE Physics 2014 paper reads as follows. The donor concentration in a sample of N-type silicon is increased by a factor of 100. The shift in the position of Fermi level at 300 Kelvin, assuming the sample to be non-degenerate, is. This is a numerical answer type question, and we have to provide our answer in units of MeV, that is milli electron volts. The value of kBt, where kB is a Boltzmann's constant, has been given to be 25 milli electron volts at 300 Kelvin. Now, note that the question specifies that the sample is non-degenerate, and we know that for a non-degenerate semiconductor, the concentration of electrons N in conduction band can be given by this formula, where EF is Fermi level, K is Boltzmann constant, EC is the level of conduction band, ME is effective mass of electrons, H is Planck's constant. So now let's say case 1, assume donor concentration is equal to Nd per centimeter cube. Now we'll also assume that each donor contributes 1 electron to the silicon lattice. Now, since each donor contributes 1 electron, that means the number of electrons in the lattice would be, so I can write, and let's call this electronic concentration N1. So number of electrons would be equal to Nd. And we also know that the concentration of electrons can be written using this formula. So this implies Nd is also equal to Nc, which is a constant, exponential of EF1. We'll assume that in this case, in case 1, the Fermi level is EF1. EC will obviously remain constant over KT. Now this is our first expression for case 1. Okay. Now, what's said that case 2, let me take a different pen for case 2. In case 2, now since the donor concentration is increased by a factor of 100, so donor concentration will now be equal to 100 times Nd per centimeter cube. Now again assume each donor atom contributes 1 electron to the lattice. So now let's assume the electronic concentration is N2. This will be equal to 100 Nd, because there are 100 Nd donors and each will contribute an electron. And again, this formula remains valid because we are still a non-degenerate semiconductor. So I can write 100 Nd equal to Nc. That remains a constant because we're not changing the temperature and the effective mass. The lattice remains the same. Exponential of, now let's assume the Fermi level is EF2 minus EC over KT. This is the second expression. Second, and we had this original expression as first. Now let's do this thing now. What I am going to do is I am going to now divide. What I'll do is divide expression 2 by 1. So let's write the LHS first. So LHS is 100 Nd. The LHS there is Nd. This will be equal to, the LHS here for expression 2 is Nc times exponential of EF2 minus EC over KT, and the RHS there is NC times exponential of EF1 minus EC over KT. Okay, ND and ND get cancelled, NC gets cancelled, EC and EC gets cancelled. So what I get is 100 equal to exponential of EF2 minus EF1 over KT. Now simply taking natural log on both sides, I'll get ln 100 equal to e to the power, sorry, since you have taken the log, EF2 minus EF1 over KT. Now let me calculate the value of ln 100. ln 100 is 4.6. So I get EF2 minus EF1 is equal to KT times 4.605. Now we know the value of KT, that's been given as 25 MeV. So I'll simply plug in this value of KT as 25 MeV and I'll get my answer to be 115.1 MeV. This is the answer that we have gotten. I'll highlight this. This is the answer that we have gotten, 115.1 MeV. This is the difference. Note that EF2 minus EF1 is the shift in the Fermi levels between case 2. Case 2 was when donor concentration was 100 times the case 1. So our answer is 115.1. We need, yeah. So it doesn't say how many decimals. So I will just provide a whole number. So I'll simply write 115. So 115 is the answer. 115 MeV is the answer and the units are MeV here. So 115 is what we'll enter in our numerical answer type question. Thank you for listening.